Everyone, in today's video we are studying the nucleus. We'll get started with the idea that the nucleus consists of protons and neutrons, and we'll start looking at a little bit of notation that is seen here and there with Z, N, and A. So Z represents the number of protons, N represents the number of neutrons, and A represents the number of nucleons. Okay, and this is kind of a new idea. Nucleons are just protons and neutrons. So A is equal to Z plus N. So nucleons are just things inside of the nucleus. The only things inside of the nucleus are protons and neutrons. So we can kind of group them up into nucleons. So let's take, for example, magnesium 1224. So by this notation, we see that A is equal to 24. That's what the 24 stands for. And then Z is equal to 12. So magnesium has 12 protons. That's the definition of magnesium. That's the idea of the whole periodic table. If we're dealing with something with 11 protons, it would be sodium. If we're dealing with something with 13 protons, it would be aluminum. So magnesium, by definition, has 12 protons, which is why we call it magnesium. Okay. From this, we can see that N is equal to 24 subtract 12. There must be 12 neutrons in this particular atom, which possesses an atomic mass of 24. Okay, so atoms can have kind of differing numbers of neutrons. So let's take, for example, these two different representations of carbon. So carbon has 6 protons, but there's a difference here. The atomic mass of this particular type of carbon is bigger, it's heavier. And so sometimes we'll be able to draw it like this. Remember, this is all just notation so that when we start getting into the lingo, you don't fall too far behind. But the first one would be considered to be carbon 12. So it's just versus the second one, which is carbon 14. So this is carbon 12 and this is carbon 14. And what you have here is a differing number of neutrons. Differing number of neutrons. Okay, and so these are sometimes referred to as isotopes. Both of these are isotopes of carbon. And there are more isotopes of carbon that would consist of a different number of neutrons. For example, carbon 13 is an isotope of carbon. Okay, so what we're getting at here is, just to recap, we have protons and neutrons, and then a total atomic mass. And you can have atoms with different number of neutrons, and we refer to those as isotopes. Now we're going to get into something a little more mathematical, and this is referred to as the atomic mass unit. This is defined has 1/12 the mass of a carbon-12 atom. So wherever the mass of a carbon-12 atom is, if we take 1/12 of that mass, we get what's called one atomic mass unit. So this is roughly equivalent to 1.660539 times 10 to the negative 27 kilograms. And I don't normally enjoy or even encourage to write numbers to this many decimal places, but when we are dealing with the nucleus, it's probably one place where we kind of have to. We have to be this precise in writing our numbers, and I'm doing our math. So that's one atomic mass unit. And we kind of start to define everything, including protons and neutrons and electrons and different atoms, in terms of its atomic mass unit. Its mass in terms of atomic mass units, if that makes sense. So let's just do an example here. We'll do the electron. And we'll do this in 2 ways. We'll do it in kilograms. In kilograms, it's 9.11 times 10 to the negative 31 kilograms. Okay, and now in atomic mass units, this is 5.485799 times 10 to the negative 4. Okay, and here I will also write the proton and the neutron. Proton 1.007276 atomic mass units. And this kind of makes sense. It's just roughly around 1 because the majority of the mass of any atom is its nucleons. And so carbon 12 has 6 protons, 6 neutrons. And so if we take a 12th of that, it should be roughly equal to 1, but it's not quite 1. More on that later. 1.67, protons and neutrons are very, very similar in terms of their mass. So proton is 1.008665. And we'll do one more here. For reference, this is quite a useful one, and so we'll call it this H11. So that represents the hydrogen atom. 1 proton, no neutrons, and we really only are going to have this one in atomic mass units. So it's 1.007825. It's pretty well a proton, but also accounting for the 1 electron that sits in there. So I guess if you kind of add these two numbers together, these first two ones, you get the 1.007825. Okay, so just having that is kind of useful. So it's kind of our table here. And now we want to look at a few interesting things. I think we've talked about this before, but we'll reiterate. kind of just how I draw a helium nucleus. Remember, a helium nucleus is 2 protons, 2 neutrons. It spans a very small distance, and that's what we were calculating in some of the last lessons. How big's the nucleus? Okay, so for a helium nucleus, it's around 10 to the negative 15 meters. Okay, and what we want to do is I want to take a look at the forces here. We want to look at it from a bit of a historical perspective. By the time they're looking at this, the early 1900s, it's pretty well just 2 forces. There's gravity, which at this level of mass, despite being very, very close, these masses should attract each other due to gravity, but if you do the calculations, we find that this is weak. It's very, very weak compared to, and so everything's relative, it's very weak compared to our electric force, or the electromagnetic force. Remember, the electric force is dependent on the charge, so the neutrons aren't going to do anything, but the protons here are going to push against each other, like charges repel. And if you do that calculation, you find out it's not really just strong, but it's strong compared to gravity. So these two protons are going to want to push against each other. And so what's really important about that is that, well, they are pushing it against each other, but there's something else that's kind of holding this whole thing together, this nucleus, if you will. There's something else here that physicists and scientists predicted would exist. And so at this point, there's really only 2 fundamental forces. We kind of group in magnetism with electric force. And so they came up with the idea that there must be a third force. A force exists that holds together the nucleus. Holds together the nucleus. And what's really important about this third force that must exist is that there's a lot of places, or I guess ranges in the universe, for matter anyway. Like this third force doesn't really interact on our scale of matter, of meters or hundreds of meters, or we don't see it interacting with planets or even or really anything other than within the nucleus. That's the only place this seems to show up, and that's really important because that's where you have to look for it. And so that force exists. It holds together the nucleus, and only kind of operates within the nucleus. I wonder what they called it. Moving on, we want to now examine, kind of put this math to use a little bit. So we're going to look at the helium nucleus. That third force, by the way, they called it the strong nuclear force. What an original name. So we want to examine the mass of helium. The whole thing, the whole atom. So, the whole atom is the 2 protons, 2 neutrons, you get the 2 electrons flying around on the outside somewhere. Okay, here's your helium atom. All right. So the mass of helium, we're going to do this in two different ways. The mass of the atom itself, the atom of helium, we can even be formal here, helium-4, was shown to be, so we say the mass of the atom was shown to be 4.002603 atomic mass units. And this is given. This is experimentally verified for a very long time before the 1900s. Okay? And that particular mass has been found for many atoms, the mass of the atom itself. So then that's the one thing we want to look at. And then we want to take those numbers that we were looking at before, and we want to look at what's the mass of all of its nucleons and electrons. So the way you do this is you have 2 protons plus 2 electrons. Okay, that's that H11 that we were looking at before. That's this. So we have 2 times that number there. Okay, so let's write that down. 2 multiplied by the 1.00785. All right, and then you have 2 neutrons as well. And you have 2 times 1.008665. Okay, so this is the atom. This is all of the things that make up the atom. And when you add up all the things that make up the atom, maybe we'll just call it the parts, the atom, you get a mass that's equal to 4.03298 atomic mass units. Now this may not jump out at you, but this is pretty profound. Trying to talk a lot about this, but it turns out that the nucleus is less mass. If you just look at those numbers, the nucleus is less mass than the sum of its parts. Less mass than the sum of its parts. That is an interesting idea. All these numbers were shown pretty well to be calculated quite accurately, and there seems to be a bit of an issue here, at least with my own understanding. This has been something that has eluded my own understanding for quite a bit of time, but I do my best to wrap my head around it, and we have some more things to formally define here, so let me do that first, and I just want to let that sink in a little bit. Okay, and the fact that there seems to be a difference here is interesting, but we refer to this is referred to as the mass defect. Okay, mass defect known as delta M. So delta M is formally equal to the mass of all the nucleons. That's what I referred to as the mass of the parts. If you take the mass of the nucleons and you subtract the mass of the atom, you get what's referred to as the mass defect. And so that's a very important equation. It's very exciting to be able to teach about some of the things that Einstein came up with. That's really exciting, to be honest. So helium 2 plus, I guess not even 2 plus, just the helium atom itself. 2 plus would say no electrons. So helium is, if we use the mass defect here, 4.03298, subtract 4.002603, you get a mass defect here of 0.030377. And it's like, even our symbols here, there's a change in mass that's not zero. There's a interesting idea here that the very act that bringing the nucleus together somehow changes the mass of all the things involved. And it's very interesting to think about. We have these laws in physics. There's conservation of mass. I suddenly don't have the analogy I always kind of come with is, let's take, for example, you have the 2 protons and the 2 neutrons. Okay, if you suddenly bring them together, suddenly their mass together is less than what their mass was separate. That's pretty profound, I think. It would be as if you set 4 chairs up at a table and all of a sudden the mass of the whole thing is less. That's interesting. It's weird, to be honest with you. This was kind of the idea. The very act that we bring the nucleus together somehow sheds a little bit of mass. This mass that gets shed is a little bit different, though. This mass defect is lost. This is lost. Mass in the form of energy. Maybe I find this particular idea interesting or weird because I'm thinking about things in the terms of solid objects with mass, and maybe I shouldn't be. Maybe at this scale of things, it doesn't work like it does at our scale of things. Things this small behave differently, and this was one of the things that Einstein had kind of noted. This is his famous equation: E is equal to mc squared. And so we can now begin to use this a little bit, because we're saying that there's a lost mass here. The mass changes by a certain amount, and that mass can be thought of as energy at this scale of the universe. So let's go ahead and do that. First off, if we start to think about this as energy, it's known as the binding energy, referred to as the energy that binds the nucleus together. Okay, so normally we have this delta M is equal to mass of the nucleons minus the mass of the atom. Okay, so if I suddenly just multiply both sides by c squared, no reason why I can't do that. I'm multiplying masses by the speed of light squared, so I'm getting energies here. So I call this the binding energy, the one that references the mass defect. And then this becomes the energy of the nucleons minus the energy of the atom. Okay, so there's a bit of a little bit more calculation to happen here. We'll do that just on the side here, but it's easy to calculate the energy. Energy is equal to M, so we call that the 1 atomic mass unit, M times C squared, so 3 times 10 to the 8 squared. And the energy you get in joules is roughly 1.492 times 10 to the negative 10 joules. We'll say per nucleon. So I'll say per A. Yeah, I think I can say per A, if that makes sense. A was our symbol for nucleon, just so I don't squeeze things in too much. This also kind of, we have another measurement of energy, call it mega electron volts per nucleon. Okay, so this kind of says, okay, for 1 nucleon, per 1 atomic mass unit, I get about 931.5 mega electron volts. For helium, the binding energy of helium is this mass defect, and then we can just very simply compare it to 1 nucleon. It's not quite 1 nucleon, it's about 1/3% of 1 nucleon of mass shed, and so that equals out to be roughly 28.29 mega electron volts. Okay. So there seems to be this idea that if I bring together nucleons, the energy changes, the mass changes, and in fact, when I do this, when I bring them together, I get the nucleus that I have, plus I get some mass somewhere else, but it's not here in the nucleus. It's given off, and it can be given off in the form of energy. So I get a little bit of energy here. In fact, I kind of get a lot of energy. And what will kind of come back to that lot of energy in a second, we want to look just a little further at this delta N. Because there seems to be a point, kind of referred to it as a turning point. The turning point, we're bringing together those nucleons, no longer releases energy. Seems to be a turning point. We're bringing together nucleons, no longer releases energy. So I'm going to say the turning point where we no longer release energy. So turning point where we no longer release energy from bringing nucleons into a nucleus. Okay, if we examine all of the atoms that we know exist, a turning point seems to happen at iron with 26 protons and 56-ish neutrons. So iron seems to be the point. So, you know, here we have our helium 4-2 that we just put together, and everything here releases energy. From just being put together. Everything past this actually costs energy. costs energy to put together. And some of these things are put together because we do have elements past iron. So just kind of bringing up what the periodic table looks like here. Here's iron. Everything past it costs energy to bring more things into the nucleus. So things like copper and silver and gold and mercury, bromine and tin and lead and uranium. All of these things cost energy. And so it's an important thing to look at. And the why that happens is very, 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 very complicated question. Just kind of looking at your periodic table. Also, these atomic masses, just for reference, if we go up to helium, helium's atomic mass is 4.0026. That's the atomic mass that we calculated. That we just were given. All of the atomic masses that you use in lots of your science courses are using the things that are defined as the atomic mass unit from chemistry. So, that being said, get back to this, and just have a little bit more here, which is, all of these things, copper and gold and silver and uranium, they all cost energy. And there's some type of, I guess, when we talk about physics, like, can we exploit this? And it turns out that we do exploit this. This costs energy to put together. So if we break apart one of these things, it might actually give us energy. So the energy that goes into putting it together, something like a uranium atom, if we split that uranium atom, we'll get the energy that went into it to put it together in the first place. So the split uranium atom will give energy. So our exploit here is our nuclear fission reaction. Nuclear fission reactor. Okay. And over here, our exploit would be the ever elusive. If I put together some things, it turns out I'll get energy released from that. It's actually how the sun works. The sun is doing this type of exploit called nuclear fusion. The sun has one advantage. It's so heavy that it's easy to put the atoms together. Gravity pushes them so close together. In fact, gravity pushes them to a place where our hydrogen atoms, these hydrogen atoms, they get pushed together to the point where they are around this close. And when they are this close, the strong nuclear force brings them together. It fuses them together, and you get a helium atom. That's kind of the reasoning why this is starting to happen. So gravity for stars smushes these protons, these hydrogen atoms, so close together that their repulsion forces, their electric repulsion forces, are just strictly negligible to the strong nuclear force, which pulls them together and holds them together as a helium atom. And this is also the reasoning why these things don't seem to want to do that. It's the reason why you have to put in energy to make things like silver and gold. As you increase the number of protons and number of neutrons, you actually increase the distances that everything is away from each other. And so it becomes more energy intensive to actually kind of do that, because your nucleus for something like, a gold atom is much bigger than 10 to the negative 15 meters. It's bigger than this, and so therefore that strong nuclear force that holds the atoms together isn't able as much to do that, and so you got to put a little more energy in to help out that nuclear force. So I hope that kind of makes sense. The whole idea of why, I hope I explained pretty good as to why there's a turning point. Why is there a particular point where there isn't energy released, but it actually costs energy? There's always this balance between the electric force and the strong nuclear force. And this ends up causing some things that we see, such as, that's why there's a lot more things like carbon and oxygen and nitrogen and iron than there are things like gold and silver and uranium. So there's more aluminum on the planet than there is gold, because the stars can fuse aluminum and release energy. It doesn't cost them energy to do that. So I hope that's kind of making some sense. One of the other side effects of this is if you take pretty much all elements along this, and this is a side effect of the strong nuclear force, but things often aren't, I guess, themselves for that long. So I guess the example being, and time is a relative idea, but uranium-235 is playing this balance between the electric force and the strong nuclear force. And so every so often, some part of uranium-235, this is just the example that I have here written down, breaks into helium-42, and it ejects a helium nucleus out of its original nucleus. So this is a helium nucleus that gets ejected from the bigger uranium nucleus, and the uranium becomes thorium-231. So that being said, this is one process that we actually call, this is an example of radioactive decay. Now this happens to every atom, because eventually those forces that are constantly battling, the electric force and the strong nuclear force, eventually kind of a misstep happens, if you will, and one of the forces wins out, and so in this case the helium nucleus gets ejected. That's how I've always thought of it. The electric force kind of wins. It gets far enough away that it's definitely complicated, but I've always thought about it this way. This happens every so often, and for different elements, it's in different isotopes, that time frame of how often it happens is very, very different. That being said, that's our kind of intro into the nucleus, and this will lead us into the fundamental thing that we call radioactivity. And that will be our next lesson.